meetup, and also maybe a bit about the history of this meetup. It's our 5th birthday tonight, so we're having a little bit of celebration. So I'll just talk about some of the talks we've had in the past, which have been amazing. So we'll take it away from there. So the data science meetup is supported by the University of Sussex. Particularly, it was started by myself back when I worked at the University of Sussex, who were setting up the data intensive science centre at the University of Sussex, which we came with the acronym DISCUS. And so DISCUS is a group within the university that crosses across departments, physics, mathematics, informatics, psychology, neuroscience, and so on. And they actually basically work with in collaboration with the university and on more applied things. So you can approach them in terms of if you want to do some research partnering with them or for consultancy. And particularly, they've probably one of the main engagements they've had at the university is actually student placements. So they have a good crop of MSc and PhD students going through there who are doing data science masters and PhDs. With Silicon Brighton are hosting this event, they're providing the equipment and the streaming and these great facilities. We're really grateful to them. So for those of you who don't know, Silicon Brighton is a community-led initiative supporting digital growth and technology groups in the region. And so we've got Alex here at the back there, who's doing a fantastic job getting us all organised, bringing this all together, and supported by a team. And so you can get in. They've got a website, siliconbrighton.com, where you can see lots of information, resources, and so on. And there's a Twitter handle. And we want, just to highlight it, so this is one of many meetups that Silicon Brighton supports locally. So you can find your favorite programming language there, apart from Rust. But tonight you will hear about Rust, so you're covered. Oh, there you go. There's a challenge for somebody. Yeah. Okay, so yeah, you can obviously you can, if you go on the siliconbrighton.com site, you'll find links to these meetups and you'll see the future meetings and so on. You get in touch with people. So they're doing a fantastic job putting together, and Silicon Brighton is supported by and is supporting technology companies in the region. Many of you who you can see there. I'm from Magique. We're members of Silicon Brighton, and we actually so we're for those of you who don't know, we're a search engine, Europe's only search engine. So we have fun competing with Microsoft and Google. So interested in this space, and so on to the main event. Actually, before that, I think I'd just mention, if you'll humour me for a couple of more minutes, I think it's worth mentioning about some of the changes we've seen in the last 5 years since we started this meetup group. So that was 2018. So what's that about? I guess it's 9 months after the Transformers paper. So I think we I'd suggest the university they set up this group because I think there was AI was going to be transformed. To be honest, I didn't expect it to happen so quickly as it has in the what we've seen in the last 6 months with the generative AI and so on. So we've seen some interesting talks. So the group's sort of gone from being in person, like it is today, as it partially is today. Then during the COVID times, we went online, and now we're going hybrid. So it's great to be able to support people. It's great people can come along, but also support people who. So welcome to those who are joining us online, and please participate in Q&A later. So what kind of things have we had in the past? It's quite amazing. And I look back at the previous talks, and we've had talks on astronomy, flooding, land usage, all sorts of machine learning topics, quantum technologies, remote sensing, terrorist network detection on social media. We had a fun one which was very popular called "Truth, Lies, Fake News and Elections" tweets in 2019. So I guess we might have a return in 2024 of that one. I think I did talk. It was the last one on ChatGPT. We even had we even had a games night one time. So we had somebody from the Open Data Institute has invented a game called Dataopolis about how you use data. So we had a fun night on that. A memorable event was in May 2020 when we Silicon Brighton organised an NHS fundraiser. And we were part of that, and we had two amazing speakers on there. We had somebody this was May 2020, remember? So we had Professor Kiss from the university talking about mathematical models of the spread of coronavirus. So obviously had a lot of interest in that particular topic then. We also had Liz Ford from the medical school talking about understanding NHS patient data. So that was very topical. And tonight we've got two more great speakers. We've got Dhruva and Lincoln. I'll let them introduce themselves to tell you about their backgrounds rather than me just, you can read there. I'm grateful for them offering to speak, and I'm looking forward to your talks. And I'm sure you'll be happy to take questions afterwards, or we can maybe do a few afterwards and then maybe together at the end. So with that, I'll hand over to Dhruva, who I think is going to do the first talk. So welcome, Dhruva.
I'll just get my slides up. All right. Yeah. All right. Well, nice to be here. Thanks for having me. Seems like a really friendly bunch of people. Haven't been here before. So I'm Dhruva. I'm going to talk about breaking models, how, why, and when. I guess I'm not really that sure about your background, so I'll try and do something. I'm trying to do something a little bit open-ended, and we'll see how it goes. So today's goals. So as data scientists, I guess most of you have experience in what I'd call data-driven modeling. My experience, my background is a little bit more in what I'd call mechanistic modeling. And I think it's just useful as a general thing to actually look at the shared insights and the differences between those two paradigms and what one can learn from the other. So I'm going to introduce a little bit of the shared commonalities and differences. No? Okay. Then I'm going to talk about some of the issues I had that I tried to deal with in a past life about interpreting mechanistic models, which I think have some consequences in interpretability of data-driven models, which is an important topic in various domains. And then I'm going to suggest some future research efforts, which I'm keen to find people interested in joining in kind of adapting what I was doing for mechanistic modeling to some data science problems that I think are of interest. Oh, now I'm speaking loudly. Wow. So a little bit about me. I'm actually a neuroscientist. So my principal relationship with modeling is to get scientific insight. I'm interested in how neural circuits function. In particular, I'm interested in Drosophila, the fruit fly, right now. So I'm not going to go into that, don't worry. I'm not the kind of scientist who runs a wet lab, though, where I actually deal with neural tissue. I'm a computational neuroscientist. So mainly, I try and understand the functional principles of the brain just using a computer and paper. And that reflects my slightly meandering path to get there, because previously I did my PhD in the general paradigm of trying to figure out how to use powerful computational models to get scientific insight, in particular their use and abuse. So the whole Superman trope, with great power comes great responsibility. We're getting increasingly complicated computational models permeating a lot of scientific spaces, and sometimes they can give great conclusions, and sometimes you can get very confident nonsense. So gonna think a little bit about that. And that's what I'm going to talk about mainly today. So I'm going to talk about some of the issues in interpretability in computational models. And from there, as I said, I'm going to go into some future directions, which, as I said, I'd be really interested to explore with collaborators or anyone interested, which relate to making and breaking hypotheses which we get from statistical models. I like XKCD cartoons, so they do much better slides than me. So I just thought I'd give you a moment to do this. It's tongue-in-cheek, don't worry. Now, what's the point of this? Any computational model, what we're fundamentally doing is we're getting a load of data. We're somehow incorporating it in a particular kind of model. And once we've got synchronized the model and the data through training or whatever you call it, we try and get some insights. So yeah, the first part of actually getting the model to incorporate the data is often called training. And the second part you might call prediction or interpretation. And what that XKCD cartoon was referring to is the temptation to actually go backwards and try and train your model and structure your model to get the insights you want to. And I guess a high-level goal of what I'm going to talk about is a way of making sure that's not implicitly happening. So let's think a little bit more concretely about what happens when we train a model. Let's say we have some neural network, or it could be a random forest, any kind of model. So any model has parameters. These are the tweakable quantities, the things you change to change the behavior of the model, change how it interprets and processes inputs. And when you feed it with data, some training algorithm, backpropagation or whatever, tweaks the parameters based on the data. That's the process of training. Until eventually, you have a model which gives predictions from inputs that reflect real life in some way. So as a toy example, I could train a neural network on a load of data about clinical data about people's lifestyle factors, like their health and their genetic fingerprints. And I could train it to give predictions on the probability of getting a particular type of cancer. That's a very standard data science exercise, right? This is a small subset of the metabolic reaction pathways that are downstream of a kind of genetic mutation that gives you cancer. So, I'm not going to interpret it, don't worry. I don't even have a clue about it. But proteins get upregulated, dysregulated. Cancer is a really complicated process. And when we do data science, usually the structure of our model and the structure of our system are entirely different. That's not necessarily a problem, but it's something we should note. So a neural network, it has a very particular structure with weights and nodes, and nodes. Doesn't look anything like the model system, but somehow through training, we get them to have similar input-output relationships. By the way, before I should interject, please feel free to interject at any point. There's nothing worse than just blankly listening to something when you lost something 5 minutes ago. Like, I'm happy to take questions or online. Now I'm going to introduce two extremal ends of modeling, I guess, which most modeling often falls in between. So the first extreme is data-driven modeling, i.e. data science, where, as I said, your model structure looks nothing like your system structure, but that's okay, because the kind of model structure that's good in data science is one that can fit anything. You want like the best, biggest neural network that can just do anything. And the point of that is pure prediction. You've got loads of inputs. You might have loads of labels if you're doing supervised learning, and you want to fit the inputs to the labels with your model. The issues with this are if your system structure looks nothing like your model structure, it's very, very data hungry. And it's only relevant for a single data distribution. What do I mean by that? Let's say I did a clinical trial getting loads of cancer outcomes in a group of people, and they all had a particular ethnicity and gender. There might be a very different group of, the relationship between risk factors and outcomes might be very different for a different ethnicity and gender. And a neural network that's purely data-driven wouldn't really take account of that. Now, ethnicity and gender are very obvious, observable factors that you might want to incorporate, but there's all sorts of, higher-level hidden factors that could also be important that a neural network or a general data-driven approach might not deal with. So advantages and disadvantages. Here's another XKCD cartoon. So what's going on here? All of these are different methods of statistical fitting. That is, we have all these scatter plots which reflect data in some way. We don't know anything about the underlying mechanism of that's generating the data. A statistical model, whether it's linear, quadratic, logarithmic, whatever, has no actual structural similarity with whatever's generating the data. Now, these fitting methods are very good at interpolating data, but they're very bad at extrapolating data for that reason, as illustrated in the cartoon. Which leads me to another flavor of model, which has its own advantages and disadvantages. You could call this data-constrained modeling rather than data-driven modeling. Other people might call it mechanistic modeling. This is when you try and build a model structure which actually tries to reflect the structure of the system you're trying to model in some realistic way. So if my system was, the downstream metabolic pathways that cause cancer from genetic mutations, I'd actually try and model those components. And I put the dotted line because you never do it perfectly. So what's the point of this kind of model? I'm going to give a slightly more concrete example than cancer. So car models, BMW, Jaguar, whoever, they spend billions and gazillions of man-years and money on making extremely complicated mechanistic models of their cars. This is, a little Simulink a cartoon of what a vehicle suspension model might look like. And you can see it's mechanistic. They're actually trying to fit all the various different physical quantities and incorporate them explicitly in the model, rather than as a neural network. So what you need data for then? If you had the perfect mechanistic model, you wouldn't need any data. It's just, you could run Newton's laws and do your mechanical equations from first principles, and you have a car. That's not realistic. Things like, for instance, the friction of tires in different conditions are very hard to get from first principles. You need data to calibrate on the quantities that are hard to actually derive. And of course, it requires massive effort and complexity compared to something like a neural network. And the goals are different. The goal of this model is not just to predict what a car is going to do. The goal of a model like this is things like design, control, and robustness. So suppose I was interested in stiffening the suspension and seeing what would happen. I can use this model, and I can actually explore that. If I want to build a control system for ABS braking or something, that system would actually need a good internal model of the vehicle so it knows when to brake and control the thing. And robustness. For instance, if I'm flying in an airplane and it has a system dealing with disturbances like wind, I better be damn sure that my control system can deal with all disturbances in a wide range that's not trained on interpolated data. It can extrapolate to scenarios that are within feasible bounds, but we've never seen before. So these kinds of models are great for that kind of thing. And the predictions are not, the point of these models are not predictions. Just checking the predictions match real life is just a form of validation. So that's a mechanistic model as opposed to a data-driven model. And the key point here is you're predicting more than you're measuring. So usually in data science, when we're fitting data, let's say supervised learning, we're learning to predict things that we're giving data on. We're just learning to predict it in new scenarios. Here, the set of things you're trying to predict is more than the set of things you're measuring. You might want to, so lots of components actually wear out and change over the lifetime of a car. You can't directly measure them, but using a model like this, you can infer from the overall dynamics of the car that, hey, the suspension's a bit soft or whatever. And that's by exploiting the structural similarity of the system and the model. So these are the kinds of models I'm more used to in science because they're more interpretable and you can use them to actually build conclusions and think about how perturbations would affect a biological system. But they have issues. And I'm going to illustrate this on the most simple mechanistic model, which is that of a pendulum that goes up and down. If any of you did like M1 in A-level or something, this is like the first kind of mechanical model you get. So you have a mass on a spring. It seems like a very weird, abstract, and strange model to choose, but it's very easy. And actually, for instance, in vehicle modeling, a lot of stuff boils down to masses on springs. Anyway, suppose you can observe this thing going up and down. So you get data on the position and the velocity. So you can see on the right-hand side, it's a damped oscillator. With a mechanistic model, as I said, you can predict more than you're measuring. So from the mechanistic model, you might actually want to predict, to infer how much the mass weighs and how stiff the spring is. Those are parameters that you could potentially measure with a mechanistic model. If anyone's interested, here's the actual equation, but doesn't matter if you're not. So what would I do if I wanted to do that kind of inference? The first thing I'd do is to train the model and the data, right? So I'd keep tweaking the parameters of my model until the model's output looked just like my observed data. And if I got the right parameter values, so I put in these values just for a joke, well, not for a joke, just for arbitrarily when I did the simulation. If I put these parameters in, I'd get a perfect fit. Great, the model has the right parameters. But you know what? If I put these parameters in, I'd also get the perfect fit. If you're interested in the equation, you can see that it's not the actual values of the mass and the spring stiffness, it's their ratios with each other that count. I could even get these values and get a perfect fit. So here I'm estimating the mass of the spring as 200 kilograms when the true thing is 2 kilograms. So I'd get completely garbage output from a perfect fit. This is called a model unidentifiability. So basically, it's a situation where even if you have perfect data, and you have almost zero, absolutely zero, almost zero training and or test error, you can still get completely garbage predictions. And that's a consequence of the fact that in these kinds of models, the set of things you're trying to predict is more than the set of things you're trying to measure. Now, that was easy to figure out the unidentifiabilities in that system because you can look at the equation. What would be the unidentifiabilities in this kind of system? It's pretty hard to actually figure out. It's an issue in mechanistic modeling. So I built an algorithm and a software package to do exactly that. So I guess the workflow is you start by training your model and then generating some hypothesis or scientific insight based on your model, whatever it is. So for instance, let's make a stupid hypothesis. Let's say we trained our model on the mass spring data, and we got the hypothesis that the data indicates that the stiffness of the spring is less than 10 newtons per meter using our model. Once you've trained it using whatever algorithm or way you like, you note the parameter values relevant to your model-based hypothesis. So for instance, that would be the spring stiffness in this case. And then you generate what I call minimally disruptive curves. Basically, suppose you have the same trained model and the same data. It's a way of doing a scalable and directed search for parameters that would break the hypothesis you've built. So it's a way of trying to break the model while keeping the same model structure and the same training data. For instance, in the case of this simple mass spring system, these are the three parameters plotted, and any point on those lines, if I take a cross-section of the y-axis, that's a set of three parameters which give identical behavior. So, and that's the minimally disruptive curve. So it's a whole trajectory of parameters, a whole line of parameters that simultaneously fit the data perfectly, but break the hypothesis potentially. So why not just actually take your model and just look at all the parameter values and see if all the parameter values work or don't work or break your hypothesis? This would be what I'd call a brute force method, or more implicitly a Bayesian method. Suppose I had a model with 2 parameters and I wanted to test my parameters at 10 values. That's 10 to the power of 2 different points I have to test, so 100 different places I have to test. Oh. Now suppose I have 10 parameters trained at 10 values. I now have 10 to the power of 10 simulations I have to do, that many tests. That's a lot of tests. That needs a lot of computing power. And if I want to do more than 10 data points or more than 10 parameters, this is called the curse of dimensionality. And it's a general problem in applied mathematics when you're trying to analyze complicated things. On the other hand, minimally disruptive curves, the trick of this is it does a directed search. It doesn't just go randomly. It's got a way of being able to kind of literally find a priori the right directions to tweak the parameters in a way to break the model hypotheses in the worst way possible. And that means that the computational burden of the algorithm scales with the complexity of your model, not the number of parameters. So it's actually applicable to quite high-dimensional big models. As I said, I'm a neuroscientist, so I'm not going to explain this graph too much, except to say this is a detailed model of a particular neuron in the lobster. We love lobster neurons because they're good at being deoxygenated and they can deal with huge temperature and pH variations. And below is a minimally disruptive curve. Basically what it's doing is it's taking a trained model, and I'm asking it, hey, look, this is a kind of neuron that spikes with a particular phenotype. It has this kind of bursty phenotype. So a neuron, if you don't know, it has electrical activity, it spikes or it bursts. And what the algorithm is doing is it's finding ways to change the parameters of the model that preserve the bursting phenotype and preserve the red line, which is calcium concentration. Don't worry about what I actually mean. It's just preserve all the desired model features I want, while changing the parameters in the worst way possible to disrupt the conclusions. In this case, I was interested in the density of what are called calcium ion channels, and has found a way of disrupting them a lot while keeping the model the same. So it's a bit of an irrelevant application for this audience, but hey, I am a neuroscientist, and this is the animation I had to hand. So now I want to get from here to the unexplored, the stuff I haven't done relating to data science that I think could be an interesting application of this and for which I'd be really interested in exploring with people here. Suppose I had a model based on clinical data where I was trying to correlate mortality to night shifts and/or smoking. Now, let's say that smoking and night shifts are correlated. People who run night shifts are more likely to smoke. It's a stressful thing. Mathematically, it's impossible to try to find the true correlations between either of these independent variables, night shifts and smoking, and mortality, because they're correlated. So you can get erroneous conclusions. To put it another way, I could get the same data and say, hey, look, I think night shifts are really, really highly correlated with mortality and smoking is not at all. Or I could do it the other way around. I could say smoking is really, really related with mortality and night shifts are not much. And both of those conclusions would fit the data if those two things are correlated. Hopefully you can see that, it makes sense. This is well known in stats. I'm not discovering the wheel here. And it's called multicollinearity. So when two variables are correlated, that's basically trying to say that there's a linear relationship between the variables. Here's another way of thinking about multicollinearity. We have our data, our clinical data on mortality based on those features. We fitted it, but there's no one single unique set of fitted parameters, i.e. correlation coefficients, that perfectly fits the data. There's an entire space of correlation coefficients, ranging from night shifts being really high and smoking being really low, to smoking being really low, night shifts being really high. And they would generate different scientific hypotheses, wouldn't they? They'd have different clinical conclusions from that. Hi. Oh, sorry, I should use the mic more. Sorry, I hope people can hear me. Okay, great. So that's a linear space of parameters. And there's standard diagnosis tools in statistics to deal with this. I wouldn't say they're perfect, but you know, they're there. Now here's a flashback to what we were talking about before, the mass spring system. Can you see a relationship? There's a whole linear space of parameters consistent with one particular behavior. Now I'm going to invent a new word, which is nonlinearity, which doesn't exist in the literature. What if instead of having a linear space of parameters commensurate with one particular model conclusion, there's a nonlinear space of parameters? Well, then it's not actually obvious. There are not standard tools for diagnosing. And this is where I think minimally disruptive curves could come in useful. Because it's not restricted to linear spaces of parameters. It weaves around the set of parameters in the model, trying to find ways to break your hypothesis. So, for example, I think I'd be interested in trying to achieve a goal in medical statistics. So, what would that be? That would be taking an existing study on, something, risk factors for vitamin D deficiency or whatever. Take the model from the paper, take the data from the paper, and then what? Use minimally disruptive curves to generate a new instantiation of the model, with the same model structure and the same or almost as good a quality of fit, but the opposite conclusion. So for instance, suppose I read a paper with a model saying that vitamin D decreases your mortality rate. Often those models are actually not very robust. They do very incomplete and bad sensitivity analyses, and that's part of the reason why clinical studies change each year in their conclusions. What I'd be trying to do is to use minimally disruptive curves to take the same model and the same data and try to find a way of tweaking the model until it can show the opposite conclusion to what I'm interested in, that vitamin D increases the mortality rate. What would be the domain of validity for this kind of thing? Well, nonlinear models, because linear models are kind of already covered with the existing literature. Those where there's a quantitative relationship between the fitted parameters and the scientific conclusion. So for instance, usually when you have one of these things like vitamin D increases your mortality rate, there is a literal correlation coefficient in that model, which when it's positive or when it's high, indicates the degree of correlation you're using scientifically. And examples, if you're interested, but don't worry if you're not, are generalized linear models or proportional hazards models, and I'm sure there's more. But those are some candidates I identified. So yeah, that would be really interesting to do. This is a bit of a side hustle for me because, as I said, I'm a neuroscientist right now. But I'd be really interested in talking to people who are interested in helping or adding insights or feedback. So yeah, that's it really. So thanks a lot for listening to me. I'd like to thank Antonis and James, who were my supervisors when I was doing my PhD and when I developed the algorithm. And Tim O'Leary, who was my supervisor when I was doing a postdoc, and was very generous to allow me in the middle of the pandemic to do this for a bit instead of doing science, because I just wasn't in the space to do science. Sometimes you just need to code, right? If you're a little bit lonely. And that's true, no? Yeah, and I'd like to thank the funding bodies. There's an old mathematical, not very readable paper about the algorithm. When I made it, the paper, it wasn't a really very reasonable algorithm to do, but recent advances in what's called differentiable programming, thanks to machine learning advances, have made it actually quite easy to implement these kinds of things. So I made a software package, and the QR code and the website are there, which implements this, unfortunately in Julia. Yeah. But so if you check out their website, you'll probably get the best view of what it's doing. So thanks very much for listening. That's it. Questions? Hi.
If you have any questions, we're going to run the mic from up here to wherever you are in the room.
Shall I give you the mic?
Oh, yeah, right. Thank you.
Maurice?
Yeah, thanks for this cool talk. So you talk about mechanistic models, but these are not causal models.
So different people mean different things by
Oh, sorry, I've got to take the mic back. Sorry, I was like, oh, that's a really interesting question.
Well, why don't you explain what you mean by causal models? Because different people mean different things.
Like
You come on down.
Judea-Pearl directed acyclic graph causality approach. Yeah.
So yeah, thank you so much. It's just for the people on the stream.
Okay, thanks. So Moritz asked the question about whether the validity of these of this algorithm is restricted to causal models, and he defined causal models as somewhere particular factors cause particular things to happen, and there's no feedback. So not something like a steering system where your position goes to the left and you turn to the right based on your position. The answer is no. You can apply this algorithm to any type of dynamical system that's differentiable. You can do it to things with feedback. It's not restricted to causal models. Sure. Why don't you just stand here? That wasn't the answer to your question.
Yeah, I think what I meant more is, wouldn't it be beneficial if you have like a notion of causality in this approach? Because right now you can apply it to every model, but wouldn't kind of trying to like explicitly include causality in some way help?
Sorry, I guess I don't know why would causality? I mean, most models are not causal. Most systems in the world, their input is affected by their output, right? Something like a model of cancer progression. Things happen and that affects upstream things and then downstream things. There's feedback loops everywhere. A vehicle control system, same kind of thing. I don't really believe in causality as a good way to think about real life systems with feedback, unless you're in a very, very simplified setting, maybe. But I don't know how it would help you philosophically here, because in the end, I'm not trying to say that there's necessarily a causal relationship. But if your hypothesis is specifying causal relationships, so there's issues in that, right? So for instance, in a statistical model, when you're doing a clinical study saying you die more if you smoke more, there is always the causality correlation issue. Maybe you're talking about that. Now, I think that's fundamentally something you can never solve with mathematical tools, right? Unless you actually have a mechanistic model of exactly what's going on, how smoking hurts your lungs, and then, that causes all sorts of downstream and upstream effects with feedback, so not necessarily causal. So it's not going to solve correlation versus causality. Nothing can solve that. You disagree, but maybe... I'm not sure if I answered your question. I feel like I might be talking about slightly different things.
Isn't there? I can feel it.
Okay,
hold on.
We can talk about it offline. It sounds
You're
interesting.
Now, yeah? Check. Sweet. Are you sure, Maurice? Because look, I'm here now. I mean, I'm enjoying the conversation. Not that I understand it, but I think it's great. Hey, Lincoln.
So I was going to say, what's your view on causation? Because in the metaphysics of causation, there's lots of kind of different approaches to causation. There's like counterfactual conditional approaches. There's like kind of more mechanistic, causal, mechanical approaches to causation. So like, what's your Are you coming from the
Are you coming from a business?
Yeah, so I guess what caused my question was when you mentioned medical studies and you essentially tried to apply this approach to like kind of like the mechanistic model that you mentioned without in the context of this medical study trying to reason about a kind of underlying causal model that you have, right? And of course you can in a system that's not like dynamic, and we can define interventions, and we can also reason about kind of the validity of different dynamic acyclical graphs as a causal model. You can try to, given the data, decide which causal model makes more sense. And especially like in the context of the kind of I think the example was night shifts and smoking. It would help if you have like an underlying causal model instead of just like curve fitting, basically. Right?
Yeah, I completely agree that having an actual mechanistic model of the relationship between things with these things would be ideal. But in real life, this is a modeling problem. I'm taking a modeling. So you're talking about how to do the right model for these things. I'm saying there's lots of models in the literature which already give conclusions out of these things without that, because in the end, that's actually really hard. How do you build a causal model of exactly how night shifts are going to increase mortality? If you look at most clinical studies, they're doing slightly unsatisfying, but nevertheless relevant correlational analysis. My problem is not to make them to build meta model structures. They should do that if they can, and probably they can't, otherwise they would have. My problem is to say, if they've generated a particular insight from their models, which may be incorporating causality as much as they can, or maybe not, how can we break the conclusions? And the reason the conclusions are often breakable are exactly the problem you're specifying, the fact that correlation doesn't necessarily imply causality.
Okay, yeah, that's a good answer. Thanks.
Yeah.
Thanks.
Oh, that felt like a natural ending to that convo, didn't it?
That went.
Sorry,
It was
should be coming
interesting.
to here, yeah. Any more questions? Be brave. Go on, Colin.
Yeah, very interesting talk. Thank you very much. I think the answer is probably going to be no, but I'm going to ask because 20 years I was involved in basically modeling things with partial differential equations, physical systems, fluid dynamics, solid dynamics. So obviously, so the underlying models are differentiable, but they're being discretized in space and time. So your methodology could be applied to those, could be, you know, actually transformational. But I'd imagine it probably doesn't. It breaks down because you're, you know, we're dealing with. No.
It would have. If I'd have said yes 3 years ago. Oh, sorry. I'd have said yes maybe 3 or 4 years ago. But for instance, okay, so you're going to talk about Rust. I was coding all this in Julia, which is an inherently differentiable language. It's kind of state of the art now for building partial differential equation models. Of course, whenever you're solving a differential equation, you're discretizing in time or space. But you can differentiate the approximation, or you can approximate the derivative. Approximating the derivative is what's standard done with finite difference analysis, that kind of stuff. But now there are programming languages which are differentiable from the level of the compiler up. So you can literally differentiate the entire program. So you build a program of your model using partial differential equations or whatever. You use automatic differentiation to get an overall gradient of the output with respect to the input. And it's pretty trivial. It's amazing. I mean, because I did spend my PhD trying to make my own hack to do this in simple ODE models, and it didn't work very well, and it was a nightmare. But now, yeah, you can solve PDEs and get the gradient of the solution with respect to parameters very easily. And that's basically because of machine learning compiler architectures and stuff that, you know, people have used.
Yeah, thanks for this talk. That was really interesting. You've been talking about the multicollinearity, and I think you have measures or methods how to identify those. I was wondering about the multico-nonlinearity, if you have any idea about how you would explore those, if you have them.
So I guess I'm proposing minimally disruptive curves as a way of doing that. Are you asking for the relevant background literature?
No, I think so would it give you something like a measure of multico-nonlinearity, something that you, or how would you inspect that a bit more?
So I don't really care about quantifying the level of it. I care about the implications of something like multico-nonlinearity in the context of a particular scientific conclusion. So if I have a model which requires the parameters of the model to be in a particular space for the conclusion to be valid, like, this correlation coefficient has to be negative, I want to find a way of breaking that. And if I can't, that's great. The model's doing well. If I can, not so good. Now, sometimes the only way to break that is finding nonlinear trajectories in parameter space, which other solutions can't find unless they're just doing a brute force search, which, as I said, isn't good. So yeah, what I'd be trying to do is to find those, thread that needle through the haystack and find those nonlinear combinations that would kill the hypothesis. Does that make sense? Was that the answer to your question?
I think it's just also really interesting to explore the type of nonlinearity as well. I mean, it's a hard task to do.
I mean, they have weird shapes. Like I did do a mathematical. I made a mathematical framework for quantifying that. I can talk about it briefly if you're interested. So are you familiar with the likelihood? Are you familiar with the likelihood ratio test in statistics? So that's where you have two different models. Let's say the same model with different parameters, and one fits it a bit better than the other. And basically, you say which model is there more evidence for? Well, obviously, it's the one that fits better. But how much more evidence is there based on this amount of better fitting? That's a mathematical way of doing it. And like all statistics, it depends on loads of weird assumptions that don't actually apply in real life. But you can think of the set of parameters for a model structure that satisfy the likelihood ratio test, and that would be a cloud in parameter space. Within that cloud, you can think of the furthest point in that cloud satisfying the likelihood ratio test. Now, you could keep increasing the diameter of that cloud by doing a more generous likelihood ratio test. And theoretically, a minimally destructive curve should trace on those points of furthest on the likelihood ratio test. I don't know if that's really easy to understand without a graph, but I can show you the maths. If you want
I know what you mean. Yeah. Thanks.
Okay, great.
Any more questions?
Hi.
Yeah, sure. Thank you very much for the talk. So taking a really simple example of, say, a CNN or something, and applying it to, say, a detector, binary classification, cats versus dogs. How would this apply to that?
It wouldn't. I guess this is why I was trying to think a little bit at the beginning about data-driven versus mechanistic models. So in something like a CNN, what do you care about? You care about how well it fits the data, and maybe the test data as well. You don't care at all about what the actual values of the weights are. They mean nothing to you. What this would do is find different values of the weights if you had a hypothesis dependent on the weights, but you don't. You have a hypothesis that depends on the output. So it's not really interesting in the context of neural networks. It's more when your model has some quantities in it that you're trying to interpret and make sense of.
Thank you very much.
Thank you.
Anyone else? Anyone feeling brave? Cool.
Fantastic discussion.
All right. Thank you very much.
5 minutes in between while we get set up for Lincoln. So please have some more pizzas, some more drinks. Fantastic.
And so before I get started in my talk, I've just been directed to do just a little bit of a plug for DiskNet. DiskNet is a doctoral training system that a scheme that exists at the university. It's been funded by the Science and Technology Facilities Council since 2017, and it's graded A as a doctoral training center. And so it's trained over 80 PhD students, and these students have been very successful, have won numerous international prizes and national prizes. And the reason why I put this, why I'm plugging this, is DiskNet at the moment, as part of the doctoral training scheme, PhD students are required to spend 3 months out working in industry. And so in the past, they've gone, for example, and worked at startups in Brighton. So there was one student that worked with a startup called DeskChair, which to develop systems for recognizing interesting objects in webcams. So I think DeskChair had cameras out on Brighton Beach. And so DiskNet is looking for partners where we can place PhD students. So if you're looking for somebody that has a really high level of training in data science, and you're willing to partner with us or and to work with us to place those PhD students, we'd love to hear from you. So there is an email at the bottom, Susan Bell, that you can send an email to if you're interested in partnering with us, or you can come have a chat to me afterwards, and I can put you in touch with the right people as well. Okay, so that's the little university plug over. So what I'm going to talk to you today about, so I'm going to talk a little bit about Rust. So Rust is my favorite programming language. I think anybody who's spent any time using Rust, it is also their favorite programming language. And so this is going to be my love letter to Rust that you guys are all going to be forced to listen to. And because you guys work with data, you're data scientists, I'm going to tell you a little bit about where I think Rust fits into the data sciences toolbox, because I certainly think it does have a place. So if we think, well, actually, before we start, I'm going to tell you what this talk is not. So it's not going to be a real deep dive into Rust. I'm going to tell you some of the things that I think are cool about Rust, but there is so much more I could tell you. I could get up here and talk for hours about how great Rust is. It's not going to be an in-depth comparison between Rust and other languages. I will talk a little bit about other languages, but it's not going to be an in-depth comparison about it. But what I am going to do is I'm going to give you a taste of what makes Rust great, why I think Rust is cool, and why you should use Rust. Some reasons why you might want to include it in your toolbox. And I'm also going to give a little bit of a showcase of where you might already be using Rust in your tech stack without even realizing it, because Rust is really getting in everywhere. So if we think about like the typical data science stack, the languages that are common, the tools that are common, Python is probably #1 in terms of the most commonly used languages in data science. R is also pretty popular. SQL, again, super popular. Those are probably the top 3. Depending on like the context, you're going to find some other things as well. Some JVM languages like Scala and Java. Some array languages like K and Q, particularly KDB+ for like high performance databases, particularly in kind of like finance. And then you will also find like other languages, compiled languages for writing high performance code. And those are going to be your C++, and Fortran. Fortran is still used. NVIDIA is still coming out with new compilers. So don't forget about Fortran. So if we think about languages like R and Python, why are they popular? Well, the reason why they're popular is they're easy to use. You don't really have to think about memory, right? These languages have garbage collectors. The runtime is going to manage the memory for you. You don't have to explicitly define types. That's apparently a good thing. it makes it easier to use the language. And you also have access to a great range of libraries. So the ecosystem around languages, particularly Python, it's great for if you want to do data science. Python is a great language for the ecosystem. But these languages like Python and R, they also have downsides. So they tend to be slow. That's the big thing, right? They're not great for writing like lightweight parallel code. Python is particularly bad. R is a little bit better. But if you're writing parallel code, you're spinning up like new processes with a whole like runtime and interpreter running in that. That's not lightweight. It's heavy. And then also the downside is that you don't have to define types, because writing code without types is actually a nightmare. When you're doing code reviews on somebody's code and you get a function that you have to do a code review on, and there's no type hints, and you don't know what the function is going to take, you don't know how it's going to behave, that is difficult. So at least Python nowadays, you can put type hints in your Python, so that makes it a little bit better. It's becoming more popular. People are realizing the value of actually defining types, but you're not getting any, you're not getting any guarantees there, because even if your types are defined incorrectly, it's still going to run. You're just going to get runtime errors. So the compiler's not going to catch you, right? It relies on you obeying your linter warnings, which some people like to ignore. So how do you get around the slowness of Python and R? Well, the easy way to do it, the hard way to do it, is to rewrite performance critical code in C, C++, or Fortran, right? There are some alternatives if you're working in Python. So there's Cython, there's PyPy, there's Number, right, which allows you to write more Python-like code, but with higher performance. There's downsides to that. It is high performance, but it's still not as performant as it could be. And lots of popular libraries take this approach where they actually write, the code in C or C++. Those are called under the hood. So you see this approach in like popular Python packages like NumPy and stuff like that. So NumPy includes a lot of C. SciPy includes some C and some Fortran. You have packages like Pandas, include some C, include some Cython as well. And in R, you have packages like dplyr, and that includes a lot of C++ code, right? But writing C and C++ comes with a big cost. And the cost is that they're terrible languages and they're hard to use. You can spend hours debugging memory faults, so seg faults, because you have to like manually manage the memory. That's a pain. The tooling around C and C++ is also pretty poor. The linters aren't that great. LSPs that give you kind of autocomplete kind of sucks in C++. Build systems also suck. If you've ever tried to like diagnose problems with like CMake, it's a nightmare. It doesn't have like easy to use tools for package management or like repositories that you can just like, how you can just pip install stuff in Python. Can't do that in C and C++. And they're not well designed for writing like high level functional style code, which is like the way that I like to program. So I like to, I'm not really a Haskell programmer, but I like to write my code kind of Haskell-like, right? And C and C++ are not really designed to do that. So if we're thinking about like writing high-performance code as data scientists, most data scientists aren't professional programmers, and just the idea of trying to like deal with that nightmare that C and C++ brings is just not worth it. Just put up with the slowness is how most people kind of deal with it, right? It's better to do that than to try and deal with C and C++. But there is an alternative to writing C and C++, and that is Rust. And so that's what I want to talk to you about how amazing Rust is. So a little bit of history about the Rust programming language. It came out of Mozilla around about 2006, started as a private project from a Mozilla engineer, but then Mozilla kind of took over the stewardship of it, and it was used in their server browser engine. Then, I don't know if you remember all the problems that Mozilla had. A lot of people were laid off, they're restructuring and stuff like that. And so the Rust Foundation was then set up to take control of Rust. So because I think that the team that was working on it in Mozilla kind of got disbanded. It has an emphasis on security, on performance, and on usability. So security is just a way that it handles memory. So C and C++, because you're manually managing memory, you can have all these kind of memory faults that are exploitable, and it's a security problem. You'd get none of that with Rust. You get high performance, so you get C-like performance. In fact, in some cases, faster than C performance. And then the usability of it is just second to none. It is an incredibly usable language that is just designed to make it easy to use. It's sometimes pigeonholed as a systems programming language, right? So people go, oh, well, it's just for writing like low-level code. I think that's a mistake. It has a bunch of features that allow you to write high-level style code, like functional style code that you might write in something. In fact, there's Ruby was mentioned earlier. There's some bits of Rust that look really like Ruby, right? Which is a really high-level interpreted dynamic language. So you can write code like that, but it's a low-level language. It's incredibly flexible. It has a macro system, not too unlike Julia's, that allow you to just like, mock up simple like DSLs or add new language features, which you can do through the macro system. And the macro system, there's no runtime cost at doing the writing macros, because it all compiles down, expands to like standard Rust code. And it has an emphasis on what they call zero-cost abstractions. So you can write high-level style code. You can use like generic functions, so functions that will take any type that matches like kind of certain constraints. You can use collections and like iterators and stuff like that. You can use macros, and all of that is going to compile down to the same assembly that you would get if you wrote your code in like more low-level C-style code. So it allows you to kind of do things in a high-level way and get the performance of a low-level language, because it is a low-level language. So what makes Rust great? So the first thing is memory safety. So you're not manually managing memory in the same way that you're doing in C and C++. You're not having to write malloc and free everywhere, because that stuff is really difficult to get right. It's really difficult to manage memory properly, which is why you get these memory bugs. So anybody who's spent any time writing C will have come across this. It's a nightmare. You want to avoid doing that. The alternative that is usually contrasted with this is to use a language like Python or R. It's got a garbage collector. The runtime manages the memory for you. You, the programmer, doesn't. The language does it for you. So garbage collection makes life easier, but you get a runtime cost because the garbage collector has to, every now and again, check whether you're using a bit of memory and free it if you're not. And you're spending CPU cycles on running something that isn't your code, right? It's something else. So Rust gets around this by having a different memory model. This is the thing that makes Rust most different to other languages. And it has this idea of like ownership. So any value that you have will have an owner, right? And any value can only have one owner. And when the owner goes out of scope, the memory is freed. So here's a little bit of Rust code. Here I'm just creating a vector. And then I'm calling that vector v1. And then I'm assigning v1 to v2. So now v2 owns that value that was previously in v1. And so now if I try to do something with v1, I'm going to get an error. The compiler just won't compile because that v1 is no longer valid, right? So this is like this ownership idea. But with ownership, you also get the concept of borrowing, right? So each value can only have one owner, but lots of things can borrow those values with a reference. And so the borrow checker, which checks your borrows, checks that you're doing the right, obeying the rules of borrowing, will check your code to make sure that the memory is being, to ensure memory safety. So here's an example where I'm borrowing something. So here I'm just making a string, setting it to S1. Then I have a function here called calcLength, and you can see the little ampersand before the variable name. So that means that I'm just passing the reference. So that calcLength is going to borrow that value. It's not going to own that value. So then I can use that value again after the function call. If I passed it as not a reference, as a value, then that function would then own that value. And when the function ends, the value would go out of scope, and so it would be dropped, right? So this is how this borrowing works. Now, the other thing that makes Rust great, or the next thing that makes Rust great, is performance. So Rust, when you assign values to variables, everything is immutable by default, right? So you can't change values after you've assigned them unless you explicitly say that you want it to be mutable. So immutability is by default. I think this is a better system than other languages. It's kind of like a functional thing. So if you've used Haskell or something like that, this will be familiar to you, where data is immutable. And because it's immutable, you can pass data between threads. It can be accessed from different threads, and you're not going to get race conditions or memory bugs or things like that. So it allows you to write parallel code really easily. So these memory safety guarantees means you just don't have to worry about a whole class of memory bugs that can occur when you're writing parallel code. Because it has these high-level features like iterators, you can just, if you want to write like parallel code where you're applying a function to, say, a vector, like you might do with like a list comprehension in Python, you can just swap out iter for par iter and it'll run it in parallel. Super easy, right? Nothing to even think about there. And then it also ships with like, in the standard library, functions for spinning up lightweight threads, similar to like Go routines if you're a Go programmer. It has JavaScript style async await for doing async things. So writing parallel code, async code, high performance code, super easy in Rust. Again, this zero cost abstraction is going to help you as well. So you can write like this high level code like iterators and using iterators, and you don't have to worry about taking a performance hit. If you want to write low-level code, you can too. So if you want to do vectorized stuff with like SIMD, so that's when you have like a single instruction that is processed in parallel on a processor across multiple data, you can do that. It's built into the standard library, right? And it's super easy. It's portable. You don't have to worry about what processor it's running on. It's just amazing and fantastic. You can use generic functions, again, super easy without a performance hit. Its type system is, I don't know, I would describe it as magical. So it doesn't have a null type, right? So in Python or R, you have nuns or you have nulls, or you have NAs or NANs, and these can cause runtime bugs. So you constantly have to like check for them to make sure that they're not there so that your code doesn't crash. With Rust, it has what's known as an option type, which is similar to a maybe in Haskell, if you've used Haskell, that has a sum and a none variant. And so if you have a function that might return an invalid or a none value, you can just make it return an option, and then you're forced to actually deal with like the possibility that there might be nothing there, because you can't process an option. So you have to explicitly check, okay, is it the none variant? Is it the sum variant? If it's a sum variant, give me the value that is inside it. Error handling, instead of using what I think is an awful system of like catching exceptions with try and accept or try catch in R, it has a result type, which is an OK and an error variant, which is similar to an either in Haskell, or similar if you use R and you've used safely from the Per library. It's similar to how that works as well. So these types they're examples of enums. So enums allow you to do pattern matching, and the compiler is going to make sure that you've come. So if you think about, so Python now has pattern matching with its, like, I think it's called the match case syntax. And R has it with like switch and case. When With pattern matching in Rust, if you're matching on enums, the compiler is going to force you to match every possible variant that could occur. So you have to do exhaustive matching. The compiler will tell you if you're not doing exhaustive matching. So you won't get runtime errors because the compiler, your code won't compile, right? So that whole class of bugs just disappears. Enums are also great for doing like object-oriented style inheritance. So I think object-oriented style programming was a mistake, and I think inheritance is one of like the big things of why it was a mistake. How do you work out inheritance between your classes? Who knows? No one's got time to think about that. But enums allow you to do object-oriented inheritance right, how it should have been done in the first place. It has a trait system which is similar to like interfaces in other languages, which allow you to define shared behavior between different types, where you can just where you don't have to write a lot of boilerplate code because you can rely on like common features between the types. And so here's just an example of some pattern matching done. So here I'm creating a vector, and then I'm trying to get the third value from that. And this will automatically return an option. And then I can say, okay, well, is this going to be a sum? And if it is, give me the value in it. And if it's a none, do something else. So in this case, I'm saying, give me a 0, right? So pattern matching with enums is fantastic. The macro system is amazing as well. You can just make the language have features that it doesn't have, right? So Rust, one of the things that Rust doesn't have, which languages like Python and R do have, is Python and R have default parameters for functions. So if you have an argument and you don't pass a value to it, it will take a default. Both Python and R have like named function parameters, so you can specify a particular keyword for its arguments. Rust doesn't have this. Rust, it doesn't have keyword arguments, and you have to define everything. But you can just write a macro that gives you that feature. So I have a Rust crate, which is what they call packages, which gives you access to a lot of like the base R kind of stats functionality from the some from the stats package and some from the R base package. And so this is like, let's say I want to use the PT, so this is for non-central T distribution. This is how I would write the how I would write the R code. I'd use these named arguments, and there's a bunch more, but I'm not going to put them in there because R is just going to give me the default. This is Rust code. The only difference here is there's that exclamation mark there because this is a macro. And so now I can write Rust code that looks identical to the R code. I can even swap it around. I can get it to behave exactly like R would behave. But this is Rust. It's going to compile down. It's going to expand to Rust and compile down to the same assembly as if I was writing just regular Rust. So the macro is amazing. You can do so much more with the macro system. So this isn't HTML. This is Rust, right? It's a Rust macro that makes it looks like HTML, right? And so this is going to compile to Rust. Rust doesn't have a pipe operator. Doesn't matter. You can just make one. So there's a macro that allows you. So if you use Julia, this kind of looks like how I think it's chain in Julia or something like that. But yeah, Rust doesn't have a pipe operator like languages like R does. You can just make one. It's fine. If you want a pipe operator, you can do it. It doesn't have infix notation either for functions. You can just make that as well, right? So you can just do anything, and you can shape the language to how you want it. In terms of usability, if you've ever written C or C++ and you've tried to decode compiler errors, it's a nightmare. This is the Rust compiler, the friendliest compiler ever. So this is the code earlier that I said you would get an error because you're using a value after it's been moved. Rust tells you that. It tells you exactly where your error is. It explains your error. Not only that, it suggests how you might fix the error. The compiler is going to tell you what you did wrong and how you could do it better. And then if I need more help, I can just ask the compiler to explain the error in more detail, and it'll take me to the documentation and it'll explain everything for you, right? No more Googling around, what does this error mean? The compiler will just tell you. The tooling around Rust is amazing. Rust ships with a package manager and a build system. So no more worrying about CMake, no more worrying about like the nightmare that is Python packaging systems, right? Rust ships with one. Rust also ships with a linter. So you don't have to like think about like Pyrite or Rough or whatever. Built-in LSP. So autocomplete and all of that, built in. Formatting, built in. So you don't have to think about like, oh, am I going to use black or am I going to use some other Python formatter? Built into Rust. You use the one that comes with the language. It's got a centralized package repository like npm or cran or pypy, so you can just install stuff super easy, all just built in. But Rust for data science. So that's why I love Rust, but why might we use it in data science? So you might already be using it if, like me, you are incredibly frustrated with pandas and you've sought an alternative. So pandas is just this kind of standard data frame library in Python. It sucks because it's slow. It sucks for other reasons, but one of the reasons why it sucks is because it's slow. It's written in C and Python, but it's still slow. But there's an alternative, Polars. And so Polars is written in Rust, but you can install it and use it just like you do pandas in Python, and it's fast. It is very fast. It's faster than pandas. It's faster than dplyr. It's faster than data table. It's faster than dataframes.jl, the Julia data frames library. So you can start using it today without writing any Rust. You can include Rust in your toolbox. So if you check out the DuckDB benchmarks, Polars comes out top, except for DuckDB, but it is their benchmarks. So you can use that today. But Polars, it's a Rust library, so you can use it with Python, right? You can use it with R if you want as well. You can use it with Node.js. But if you want to write some Rust, you can do kind of weird things like this. So I've taken Polars and I've compiled it to WebAssembly. So this is not, there's no SQL server running here. I have a static server with a CSV file on it, and compiled to WebAssembly running in this browser, right? Not on a server somewhere, actually in the slides. I have a SQL query engine, so I can write SQL queries, and it's going to query that static CSV file. So I can just actually run this query. Whoop. And it'll just run that query, so I can write SQL. There's no SQL server, so usually you wouldn't expose this to the internet, allow people to like write raw SQL queries to your server. But there's no SQL server. This is just running in the browser. There's also great, an increasing ecosystem for packages that are relevant for data scientists. So there's a crate called NDArray, which is kind of like a NumPy alternative. It's designed to be very similar to NumPy. It includes all the basic functionality that you'd expect, including powerful tools for linear algebra. Using that, you can build machine learning and statistics frameworks in Rust. There's already some of this being built. So there's a crate called Linfer, which makes use of NDArray that provides a lot of the functionality that you get in sklearn, including things like PCA and ICA and SVM and lasso and ridge and all of those things that you might want to do. Decision trees, logistic regression, all in Rust. And there's bindings for things like the GSL, the GNU Scientific Library for libtorch, which runs PyTorch. There's crates for doing like automatic differentiation, Gaussian process regression, all of that kind of ecosystem is growing all the time. There's other cool things like SurrealDB, which is like kind of a next gen, like SQL-like database. There's a language written in Rust called Prequel, which compiles down to SQL, but includes far more power to do other kinds of cool things as well. Other like Rust tools that you can use now, so include things like Pydantic. So if you use Pydantic for doing data validation, it's kind of slow. The current version, version 2, is going to be maybe 50 times faster because they've rewritten the core in Rust. If you use Hugging Face models for doing kind of language model stuff, Hugging Face's tokenizer is written in Rust. If you're trying to lint large code bases and you're struggling with like the current Python linting tools, there's a Python linter called Rough, which is now being picked up by a lot of large Python projects, written in Rust, so it's super fast. If you like Julia, installing Julia and managing Julia installations is kind of a nightmare. There's Julia Up, which allows you to manage your Julia installation with Rust. There's Rye, which is a package manager for Python written in Rust. There's other tools like DataBend, which is a open source Snowflake alternative. So if you use Snowflake, if you're data engineers and use Snowflake, there's an open source alternative for that. Another thing that might be interesting for data engineers is Cube. It's kind of semantic layer for building data applications, also written in Rust. There's Rust crates for taking models, so trained models from, say, sklearn or XGBoost. So you can train those models, compile them to Rust, and so you can run your inference in Rust. So you can compile it. You can do things like compile it to WebAssembly and put it in the browser, right? You don't have to have a server that's running your inference. You can run it in the browser, or you can run it in, run it far more efficiently. So there's lots of cool things for data scientists that is happening in Rust, and more of it is happening all the time. But Rust is great, but one thing that Rust isn't great for is interactive programming, which you might do a lot of as a data scientist, where you're kind of exploring stuff. There is actually a Rust Jupyter kernel, so you can run Rust in a Jupyter notebook. But it's not great because as a compiled language, it's a little bit slow because it has to do that compilation step. So what you might want to do instead is, include Rust within your current kind of Python or R workflow. But it's super easy to do that. It's super easy to call Rust from these languages. You can call Rust from any language that speaks C, which is most of them. So that includes things like Python, R, MATLAB, and Julia. For some of these languages, you have to write the C code yourself. So if you want to know what that looks like, I got a couple of links down there. I have a blog post for how to do that for R. And if you are unfortunate enough to use MATLAB, I have a MATLAB package as well, which is written in Rust that shows you how to write that C glue code so that you can call Rust from MATLAB. But you don't have to, if you're using R and you're using Python, you don't have to write the C yourself. There's a package called Pyo3, which allows you to write Python packages in Rust. It builds the wheels for you. It even includes the CI code to build the wheels on CI. The tooling around it is amazing. It's super easy to use. So if you want to write Rust code to use in your Python packages, Pyo3 is the definite thing to check out. In the R space, there's Extender that allows you to write R packages in Rust. You can pass R types back and forth between Rust and R. You can even call all like the C code that runs under the hood when you run R with a crate called libsysr. And I've got a macro package in Rust that allows you to write essentially code that looks identical to R code, but it's actually Rust code that allows you to write high performance packages in R using Rust. And if you try to write high performance packages in R and you've tried to use something like RCPP to write in C++, that's pretty good, but some of the things, particularly around like numerical optimization, things like that, that's actually terrible, and you have to use another package called, I think, RCPP numeric, and then you have to write code which doesn't look anything like R code. But with my macro package, you can write Rust code that looks like R code, but it's Rust, so it runs fast. So just an example of how fast it runs, there's an R package called BFDA, and it's used for doing sample size planning for base factor analyses. It's not super important exactly what it does, but how it works is it runs simulations, and it's incredibly slow. So to run like a single set of simulations, to do one sample size plan, how many participants do I need? How many samples do I need to collect to be able to do this analysis? It can take up to 6 minutes to run. I rewrote it in some slightly better R, and I got the time down to a minute. But a minute is still slow. So what I did instead is I rewrote it as a Python package, but all the computations are actually done in Rust. And so to use it, you just use it like you use a regular Python package. So I can just you can just pip install it, then import it, and then run it. So and it's going to spit out a array of tuples. I'm just going to turn it into a pandas data frame, right? And this now runs the simulations in 1.5 seconds, right? So instead of a minute, 1.5 seconds, a massive speed up, right? And you can just call it as easily as you call a Python package. And not only that, it was super easy to write because you can write it in like a high-level style code. And you can actually, the added bonus is you can use the C libraries that are included in R to do some of the numerical, the probability distribution stuff, which is actually the approach that Julia uses as well. And so you don't have to rely on like the statistical distributions that ship with SciPy, which kind of suck, particularly the non-central T distribution. So an easy, massive speed up. Okay, so I've talked a lot about Rust. So where does Rust fit in? I've talked about Rust because I love Rust, but I also think it's useful for you as a data scientist. But the primary place where it's useful, I think, is in writing high-performance library code. So if you're writing libraries that are going to be used throughout your team, writing internal tools, or throughout your organization, I think Rust is a good language to write it in, right? Particularly if you work, I know Jeremy's not here, but he works in like a polyglot organization where he has some Python programmers and some R programmers. You can write libraries in Rust and then call it from Python or R, write once, run anywhere. If you like writing functional style code, which I like writing, Rust is great for that as well. I think it's better for handling data. If you want to write parallel code, again, Rust is going to be great. If you're parsing data, so if you're dealing with JSON or XML or stuff like that, Rust type system and its ecosystem, particularly this crate called nom, are fantastic for doing parsing, right? It makes parsing a breeze and it's fast, and you can deal with things like streaming data. Again, it's trivial, it's easy. Rust makes it possible. So if you find any of these things appealing, I really recommend that you check out Rust. Ferris will thank you for it. And there's a link to the slides if you want to click on some of the links, if you want to find out more about some of the things that I've talked about. And that's it.
Who's got some questions?
I don't think we have time for questions.
Ready. There we go.
Okay, thanks. That was really interesting. So the whole memory management system is really, really elegant if you want to do manual memory management. If you don't, and I don't know data science workflows, but I guess you don't necessarily, are there any advantages over Julia, which is easier, definitely, right? Because it's quite a cognitive burden to learn that. Maybe the WebAssembly stuff?
So I think in some situations you definitely do want to not run up against a garbage collector. So I think in say things like machine learning and stuff like that, you maybe want to avoid a garbage collector. If you're dealing with streaming data, again, you maybe want to avoid a garbage collector. And so in that, I think you'd want to manually manage the memory. And so I think like the borrow system in Rust makes it kind of easy. So I don't know if any of you have heard about Mojo, which is like a new kind of Python style language that's coming out, like marketed as like the language for AI, it borrows Rust's memory management system. So I think the cognitive load for managing memory in Rust way is actually way less than you would think it is.
Okay.
And then there's also, so which I didn't talk about, you can also do reference counting as well. So you can do like kind of like garbage collected style code in Rust as well. You take a bit of a performance hit, but you can do that as well. But I like Julia. I think it's a great language. But I think if you're writing libraries, Julia is maybe not the language that you're going to write them in, unless you're only using Julia, right?
Yeah, I agree.
Yeah.
Anyone else? Go on, Moritz.
So I would love to drink the Rust Kool-Aid and join you, but it seems like a lot of Python has this great ecosystem. Like there's just a package for everything, and rewriting some of these packages in Rust, I feel there's like a danger that this removes the people that use the package, like in some Python workflow, from kind of a deeper understanding of what the package does. Because like if you get some weird Rust error when you call this this library, you might not be able to understand it because you're just used to Python.
So I think there's kind of two things that you can do. You can change your entire kind of stack to only write everything in Rust, or you can just use Rust as part of your Python packages. So already there's things, there's a lot of Python packages that call C and C++, right? So the alternative is, I think, is to use Rust in place of that. And then it's up to the package developer to make sure that when it spits out, because it's going to spit out Python errors, it's not going to spit out like Rust errors, right? The way that because you're not going to get compiler errors and you're not going to get like certain kinds of runtime bugs, because there's a whole class of bugs that just don't happen in Rust. So you're not going to get things like seg faults and stuff like that, which as a Python programmer, you might go, oh, what's causing this? That's just not going to happen in Rust. In fact, it can't happen in Rust because of the memory guarantees. And then you as the package developer, if you're writing a Python package that's calling Rust, it's your job to make sure that the errors that come out are understandable for a Python programmer, right? And so there's already, like I said, like Pydantic, Rough, Polars. These are all like Python packages, right? They're perfectly usable for Python people, but they're written in Rust. Drink the Kool-Aid.
We do have a question from online. Are you up for hearing that?
Sure.
Fab. Okay, so from Vlad Vakulin, sorry if I'm not saying your name correctly, does the ownership system in Rust work as pointers in C/C++, i.e. I can pass the pointer of the variable to a function instead of the value itself?
Yeah, so you would pass a reference rather than the value, right? And so that you would allow a function to borrow it, to borrow a value by passing it as a reference. You can also do things with raw pointers and stuff like that in Rust as well, but you don't get the memory guarantees. And so you have to wrap your code in like explicitly unsafe blocks. But I think the closest analogy to C is to pass references rather than values.
Fab. Okay, so we're nearly running out of time, so we've got one more question, if that's okay.
Can you do dynamic type inference? Can the compiler do dynamic type inference or stuff, or do you have to strongly type everything?
So no, it does do type inference.
Okay.
It does. It's not like, I guess it's not like OCaml level of type inference, which is probably like the gold standard of like type inference, but it does pretty good type inference. So you need to define types for function signatures, so what it takes in and what it returns, unless you're using generics. But in terms of like the rest of the code you're writing, you can get away most of the time without defining types, because it will infer the types. Yeah.
Any bonus quick questions? Someone who hasn't had a chance to say anything and they really want to? Okay, back to Colin for the close.
Well, thank you, Lincoln. Very interesting talk. I'll have to look at Rust next time I go back to programming. There's only one downside. Not good for interactive computing. There must be other downsides, but it's no good point in asking you, I think. Anyway, I just want to wrap up by saying thank you for the team at Silicon Brighton. Brilliantly organised event. All went very smooth. Thank you very much. Thank you, everybody, for coming and for your questions. Great to see you all. Thanks to Dhruva and to Lincoln for the talks. We will be organising another meeting. I hope we've not decided yet when. We do have some speakers lined up, but we'd like to maybe we've got complement them with some other speakers. So if you want to do interested in doing a talk, we'd be either get in touch with me or Lincoln or Silicon Brighton and let us know. It doesn't have to be highbrow. If you're just starting a project, you want to get some feedback. We've had people in the past who've done projects which have been said, look, I'm doing this. I want to share it and get some feedback. So don't be shy. So please come forward and if you want something you want to talk about. And so, yeah, thanks again for coming and have a great rest of the evening. Thank you. Thanks to you. Thanks to everybody who joined us online. Thanks everybody.